stop right here when you're done. Okay? All right,
Okay.
go for it.
Thank you.
You can edit that first part out.
Okay, awesome. Hi, everyone. So today I figured that I would record this lecture because I know that we might have to go to the pack and it's a pretty difficult concept. So I wanted to make sure that you guys can rewatch it if you need to. Ms. Halstead helped me do this. So thank you to Ms. Halstead. So today we're going to be talking about friction. We did the friction lab yesterday, so you already know kind of what goes into the force of friction and what affects it. So we know that friction acts on materials that are in contact with one another, and it always acts in the direction to oppose motion. So here we can see that the motion is going this direction, and that means that the friction is going to be going in the opposite direction, all right? And this is the motion or the intended motion. So if the object isn't actually moving, then if it's being pushed in this direction, even if it's not moving, the friction is still in the opposite direction of the intended motion. Now the friction equation is the force of friction is equal to mu. That's how you say that weird little kind of m/u thing. It's a Greek letter. So mu times the normal force, where mu is the coefficient of friction, and the normal force is, if it's on level ground, it's equal to the force of gravity. But then, of course, if we have forces at angles and things, it's not always equal to the force of gravity. So we'll have to find that from the free body diagram. So this is your friction equation. Make sure you have this written down in your notebook because we're going to be using it a lot in this part of Newton's laws. So the magnitude of the friction force depends on the type of material in contact, and this has to do with that mu. You guys saw this in the friction lab yesterday. So the friction lab, you saw that the concrete had the highest friction force, and that's because it has the highest mu. Okay, that little mu thing. So the type of material in contact and how much the surfaces are pressed together. So if the surfaces are pressed together a lot, it's because the object is heavy and therefore the normal force is high. So mu, if we look at that equation again, if mu is high or if normal force is high, then the friction force is going to be high. So that's what it depends on, the surface type and how much those things are pressed together. Heavier objects are going to produce more friction because their normal forces are bigger, like I said. And this is why we have concrete barriers when you're driving on the freeway or something like that. We're kind of moving away from these metal barriers right here because the mu between the tires and the concrete barrier, that is a higher coefficient of friction than like this metal on this metal right here. So because of that, the cars can slow to a stop quicker, which is good. It causes less accidents and all that good stuff. So when we're moving at a constant velocity, like you guys saw in the lab yesterday, the applied force will be equal to the friction force. So here our net force is 0 because we know that from Newton's second law, which is the net force equals mass times acceleration, if our net force is equal to both the applied force and the friction force, and we're going at a constant velocity, that means that our acceleration equals 0 with constant velocity. So therefore, our net force is 0. So when we have this, friction force is equal to applied force. So that's a very common occurrence in these problems, and I just wanted to point that out so that you can use that. And you guys saw that in your friction lab from yesterday. So let's do an example. We have a 50 kilogram crate is being pushed on a horizontal floor at constant velocity. Given that the coefficient of kinetic friction between the crate and the floor is mu k equals 0.1, what is the push force F? So first and foremost, we want to draw a free body diagram. We have our block. We have an applied force or our push force F. We have the friction force going in the opposite direction because we know the friction force always opposes the motion. Our normal force is upward and our force of gravity is downward. So here we know that we have a net force, and that's going to be equal to mass times acceleration, Newton's second law. Now we also know that the object is moving at constant velocity. So because of that, acceleration equals 0. So because acceleration equals 0, that means net force equals 0. So net force in this case is equal to 0. Because of that, we know that our forces are balanced. So forces are balanced, which means applied force is equal to friction force. In terms of equations, we can say F applied minus F of friction, force of friction equals 0. So adding force of friction to both sides, we get the applied force is equal to the friction force. So we want to know what that applied force is. So now what we're going to do is we're going to plug in our new friction equation here. So we get the applied force is equal to mu times the normal force. Now if we look at our free body diagram, we can see that the normal force, which is right here, is equal to the force of gravity, because again, those two things are also balanced forces because we're not accelerating in the y direction. So because of that, normal force is equal to force of gravity. So we can now plug that in for normal force. So we get mu times force of gravity. And then we know that force of gravity is equal to m times acceleration of gravity. So we can plug that in for force of gravity. We get mu times mass times acceleration of gravity. And then now we can finally plug in our numbers. So we get mu is 0.1. I'm running out of room here. 0.1 times the mass, 50 kilograms, times the acceleration of gravity, 9.8 meters per second squared. And so for this, I'm going to do it on my calculator, 0.1 times 50 times 9.8, and we get 49. So that therefore our applied force is equal to our friction force, which is 49, and our unit is newtons. So that is our answer. All right, so that's our push force. So that's the first example. Now let's do another example, a little bit more difficult. So we have a man pushes 100 newtons on the handle of a 40 kilogram lawnmower. The applied force is in the same direction as the handle, which is tilted 35 degrees relative to the horizontal. The coefficient of kinetic friction is 0.1. Find the amount of acceleration. So we're given a bunch of different things here. Number one, we're given that the applied force is 100 newtons. So this is going to be our F applied. And that is at an angle of 35 degrees relative to the horizontal. I will draw this for you guys so you know what I'm talking about there. We also are given that the lawnmower has a mass of 40 kilograms. So this is the mass of the lawnmower. And then we're given that the coefficient of kinetic friction is 0.1. All right, so that's our mu. Let me write that down. That's mu. All right, so let's draw our free body diagram. I'm going to draw it up here, so because we're going to draw a new one because we know we have a force at an angle. So what's happening here is I have my lawnmower like this. We have the, let me erase that and make it farther down. So we have our lawnmower here. We have an applied force downward, all right, and that is at an angle of 35 degrees. We have our normal force upward. We have our force of gravity downward. And then because the applied force is going down this way, that means that we have an x component that's to the right, and we have a y component that's down. All right, so we're going to have to split that up into x and y components. But what this tells us is that because we have an x component of the applied force to the right, our friction force has to be in the opposite direction. So that's our friction force will be to the left. All right, now I'm going to redraw that free body diagram, but I'm going to split that applied force FA up into x and y components. So if I redraw that free body diagram, I have my force applied X, I have my force normal still up, I have my force gravity still down, and then I have my force applied Y downward as well, because that's a Y component of my applied force. And then I have my force of friction to the left. So now what I have to do is split that applied force up into x and y components. So I'm going to do that up here. So force applied x is going to be, I can see here that the x component of that applied force is the adjacent side to that 35 degrees. So therefore it's going to be the cosine of the angle. So I get its force applied times the cosine of the angle, which is 100 newtons times the cosine of 35. All right, so if I do that on my calculator, I get 100 times the cosine of 35, which is 81.9. So force applied to X is 81.9 newtons. Sorry, that's a weird N. My force applied Y, let me erase this right here so that we can see. Force applied Y is going to be the force applied, which is 100 newtons, times the sine of 35, which is 100 times the sine of 35, 57.35, so 57.4 newtons. And then now that we have that, we can now finally do our Newton's second law equation. So I have Newton's second law, net force is equal to mass times acceleration. Acceleration is what we're trying to find. So the net force in the x direction is what's causing the acceleration. So it's going to be the applied force in the x direction minus the friction force, because that friction force is in the negative direction. So applied force in the x direction minus the friction force is equal to mass times acceleration. Now, here we already know the applied force in the x direction. We know what the mass of the lawnmower is. We want to know acceleration, but we don't know what friction force is yet. So let's find that first, and then we can plug it into our equation to find our acceleration. So in order to find friction force, we want to look in the y direction right here. So we can see normal force is upward, and force of gravity and applied force in the y direction are downward. So here, normal force does not equal force of gravity. Normal force actually equals the force of gravity plus the applied force in the y direction. So in order to do that, we do net force in the y direction equals mass times acceleration in the y direction, which is 0 because we're not accelerating. So like I said, normal force upwards is positive minus the force of gravity minus the force applied in the y direction equals 0. So therefore, normal force equals force of gravity plus force applied y. Force of gravity we know is mass times the acceleration of gravity, so I can plug that in. I get normal force is equal to mass of the lawnmower, 40 kilograms, times acceleration of gravity, 9.8 meters per second squared, plus force applied in the y direction, which we found to be up here, 57.4. So I plug that in, 57.4 newtons. And now I find my normal force from using my calculator. So 40 times 9.8 plus the quantity 57.4. And I get a normal force of 449.4. And then finally, I can now use this equation right here to find my acceleration. So plugging my numbers in, I get force applied in the x direction from up here, 81.9, and that's going to go right here. So I get 81.9 newtons minus the force of friction, which I found right here. So we get 449. Oh, sorry, the force of friction, which is mu times the normal force. We know that. So we have to plug in mu first. So mu we found to be 0.1, or they gave us it's 0.1, times 449.4. Let me erase that. Oh, no, that's the highlighter. Whoops. 449.4. And that's going to equal the mass of the lawnmower. And here I'm running out of room. Mass of the lawnmower is 40 times acceleration. So here I'm going to do this side first. So in my calculator, I have 81.9 minus 0.1, the quantity 0.1 times 449.4. And then I'm going to divide that whole thing by 40 to get acceleration on by itself. So I end up getting that, that acceleration is equal to 0.924, and our unit is meters per second squared. And that's our answer. All right, so a little bit more complicated because now you have that force at the angle and you have to first split it up into x and y components. And then because of that, you have this y component down here. So your normal force does not equal your force of gravity in this case. All right, and that's going to always happen when you have a force at an angle. All right, so let's do one more example with a force at an angle. So I have Miss Stewart is walking her neighbor's cat again. Sorry if you're sick of my cat problems. And surprisingly, the cat doesn't want to be walked. I don't know why. If Miss Stewart pulls the 5-kilogram cat with a force of 15 newtons at an angle of 45 degrees to the horizontal, what will be the cat's acceleration? So we have a mu of 0.12. And again, we want to draw our free body diagram. So we draw our free body diagram of this cat. I'm going to draw it over the cat. So let's do it in a different color. Here's my free body diagram. The cat is being pulled up at an angle of 45 degrees, and that is 15 newtons of force. We have normal force upward, and we have force of friction going in the opposite direction, force of gravity downward. So now we're again going to find the x and y components of that force. So the force applied in the x direction will be 15 newtons times the cosine of 45. So 15 times the cosine of 45, we get 10.6 newtons. And then because this is a 45, 45, 90 triangle, our y component is going to be the same. But 15 times the sine of 45 is going to be exactly the same as cosine. So 10.6 also. Now, if we draw our new free body diagram, we now have a y component that's upward. So F-A-Y up. Our normal force is still up, force of gravity down, force of friction to the right, and force applied X to the left. So now you can see instead of being pushed downward like the lawnmower was, our force applied Y is upward because we're pulling up on that leash. So that means, let's find the normal force first, because we know we're going to have to do it anyway to find the force of friction. So that means that if we know and we can see that these forces are balanced in the y direction, you can say that these two forces added together are equal to the force of gravity, because again, these forces are balanced. Again, like we did before, remember we did the net force in the y direction is equal to 0, and then we plugged in our signs, and then we said these things are balanced. Here, if you want to just skip to our F-A-Y plus force normal is equal to force of gravity, it's like the same thing. So we're just going to skip forward to that. So normal force is then equal to the force of gravity minus the applied force in the y direction. So now we get the force of gravity, which is the mass of the cat, 5 kilograms, times 9.8 meters per second squared, minus the force applied in the y direction, which was 10.6 newtons. So that tells us that the normal force will be equal to, doing a calculator, the quantity 5 times 9.8 minus 10.6. We get the normal force is equal to 38.4 newtons. All right, and so now we're going to use that in our Newton's second law equation to find our we're finding the magnitude of the friction force. All right, so the magnitude of the friction force, that actually, oh, my bad. We need to first find the acceleration. And then we'll find the magnitude of the friction force as we go. So we have a normal force. I'm going to put that up here because I need to erase so I have room, 38.4 newtons. And then we're going to erase all this stuff down here so we can keep going. All right, let's see. We now have the net force is equal to mass times acceleration, because again, we're finding acceleration here. Net force in the x direction is the applied force in the x direction minus the friction force, and that's going to be equal to mass times acceleration. Applied force in the x direction we found to be 10.6 newtons minus the friction force, which, remember, friction force is equal to mu times the normal force. So mu in this case was 0.12, so we're going to plug that in, 0.12. And then the normal force was 38.4 newtons. And that's going to be equal to the mass of the cat, which is 5 kilograms. Times the acceleration. So now doing this in my calculator, we get 10.6 minus the quantity 0.12 times 38.4. You want to put that in parentheses. And that's 5.992. And then I'm going to divide that number by 5 to find an acceleration of 1.198. So about 1.2 meters per second squared. So that's our acceleration. And then down here, it asks us for the magnitude of the friction force. That's just going to be this equation right here. So if we want to find the magnitude of the friction force, it's just that 0.12 times that 38.4. So friction force equals 0.12 times 38.4 newtons. It's the mu times the normal force. So we get 0.12 times 38.4, and that is 4.6 newtons for the friction force. All right. All right, let's talk a little bit about static and kinetic friction. Static means not moving, kinetic means moving. So the coefficients for static and kinetic friction for the same materials are different. Now this is because the coefficient of static friction is greater than the coefficient of kinetic friction. And you guys should have seen this from the lab yesterday. It's harder to get something moving than it is to keep it moving. If you've ever tried to push a couch across carpet like these two guys are trying to do, it's really hard to start that couch moving, but once it's going, it's not as hard. So the static coefficient of friction mu s is going to be greater than the kinetic coefficient of friction mu k. Now we have these equations right here. The reason that we have this symbol for the static friction is that if I say I have a box and I'm pushing it with a force applied of 20 newtons, but say my maximum static force of friction is say like 50, right? Because I don't know, my normal force, I know friction force is equal to mu times normal force, and say my normal force is 5 newtons. I'm sorry. Say my normal force is 500 newtons, and my coefficient of static friction is 0.1. That means that my friction force, maximum static friction force, would be 0.1 times 500 newtons, which my maximum friction force would be 50 newtons. So if I had a friction force maximum of 50 newtons backward, that doesn't make sense that this friction force would be greater than my applied force. Okay, it's not going to accelerate this way because the friction force can't cause that object to speed up in the friction force's direction. So here we have this symbol right here because that friction force static is going to be equal to the applied force until you get to that maximum point, which is what we found right here. All right. Now, when we have two forces that are acting on a book at rest on a table, say we have its weight, mass times gravity, and then we have the normal force upward. If I'm not pushing this book at all, it's just sitting there on the table, do we have any friction? Your answer should be no. All right, the friction forces are only occurring when an object tends to slide or is sliding. Now I have one more example here, but I'm kind of running out of time. So we're going to do this example in class later, not right this minute. So we'll do it later. All right. I almost finished. How do I stop?